Today I'm going to talk to you about buffers and how to choose an effective buffer, how to recognize a buffer, and how buffers regulate pH. So let's begin with what a buffer is. A buffer is a solution that resists a change in pH by neutralizing added acid or added base. And so in order for a buffer to work, it contains either a significant amount of weak acid and its conjugate base, or a significant amount of weak base and its conjugate acid. Okay, so there are four characteristics of a buffer. The first is that it resists changes in pH, which I just said. The second is that it contains a significant amount of either weak acid and its conjugate base, or a weak base and its conjugate acid. The third is that the weak acid that's present will neutralize any added base. And the fourth is that the base that's present will neutralize any added acid. Okay, so the reason this works is because of something called the common ion effect. So if we have the balanced equation that I've put in here, this is acetic acid reacting with water to make H3O plus an acetate ion. So the calculations we've done thus far, we've just added a certain amount of acid, and then we've calculated what the pH is, right? And some of it, a very small portion, goes to the conjugate base on the other side. In this case, we're adding approximately equal, or in this case exactly equal, amounts of the acid and its conjugate base. And the result of that is that the reaction doesn't shift one way or the other very easily, because we have a lot of both on either side. Okay, so the common ion effect is named that because the solution contains two substances, in this case HC2H3O2 and then the acetate ion, and they are in common. So both of those contain the acetate ion, and so because of the Le Chatelier's principle, we don't get a shift in one direction or the other very much, which results in a very small change in the H3O plus concentration, which is how we get our pH. So now let's take a look at this in terms of calculating the pH for the same equation that I just showed you before. So if we have a solution that is 0.1 molar acetic acid and 0.1 molar acetate solution to begin, now we're going to have to make an ice table, and we're going to assume that the initial H3O plus is about 0. Right? So the change is going to be minus x, plus x, and plus x. And the reason we know that is because we currently have no H3O plus, so we're going to have to make some of that. We can't use any of that up because there isn't any present. Okay, so then our equilibrium concentrations are going to be 0.1 minus x, x, and 0.1 plus x. So we plug that into our Ka equation. In this case, x is small, so we can ignore it. So we end up with x times 0.100 divided by 0.100, and the x's, or the 0.1s, sorry, just cancel out. So x is equal to essentially the Ka for this reaction, which is 1.8 times 10 to the minus fifth. All right, and so then we can just get the pH by doing the negative log of that, which is 4.74. Okay, and so what you might notice is that this is the pKa for this reaction, because we have we've just taken the negative log of the Ka. And so this leads me to the Henderson Hasselbalch equation, which simplifies these calculations, simplifies the calculation of pH for buffers immensely. So you aren't going to have to do ice tables for those. Isn't that exciting? Okay, so because we're making the assumption that x is small and we can ignore it, then the concentration of H3O plus is just going to be equal to the Ka times the concentration of Ha over the concentration of A minus. All right, and so for if we wanted to take that one step further and solve that for the pH, we get that the pH is equal to the pKa plus the log of the concentration of base over the concentration of acid. Okay, so we simplified it to base and acid instead of Ha and A minus, because we could also do this with a weak base and its conjugate acid. So in either case, either the base or the conjugate base will go in the base part here, and then either the acid or the conjugate acid will go in for the acid. All right, so this is the Henderson Hasselbalch equation, and it is valid as long as we can assume that the value of x is small. Okay, so anytime you would be able to make that assumption, you can do this. Of course, you can always do these problems using ice tables. This just simplifies it quite a bit. So let's do two examples. The first, we have to calculate the pH of a buffer solution that is 0.50 molar benzoic acid and 0.150 molar sodium benzoate. And the Ka for benzoic acid is 6.5 times 10 to the minus fifth. Right, so to do this calculation, we have the pH is equal to the pKa plus the log of the concentration of base over the concentration of acid. Okay, so our pKa is going to be the minus log of the Ka, and then we'll have plus the log of the concentration of base is going to be the conjugate base here, so that's 0.150, divided by the concentration of the acid, which is 0.050. All right, so if we solve the first part, we get 4.187 plus 0.477. All right, and that's going to give us a pH of 4.66. Okay, so it was I think, a much simpler way to do this than doing an ice table. All right, and now we'll do one more. Calculate the pH of a buffer solution that is 0.5 molar NH3 and 0.2 molar NH4Cl. And so for ammonia, the pKb is 4.75. All right, so for the Henderson Hasselbalch equation, we need the pKa. And if you remember, the Ka times the Kb is equal to Kw, which is that 1 times 10 to the minus 14th. And so it's also true that if you add the pKa and the pKb, you should get 14. So in this case, we can just do 14 minus 4.75 and get the pKa is equal to 9.25. Okay, and then if we plug that into our equation and that acid and base concentrations, we get pH is equal to 9.25 plus the log of 0.50 over 0.20, right? And that's because NH3 is a base, and then its conjugate acid is the ammonium chloride. Okay, so we get that equals 9.25 plus 0.398, and we get a pH of 9.65. Now that I've told you about buffers, I'm going to talk to you about some of the factors that affect how effective the buffer is. So certainly the amount of acid and base that are present is going to be an important factor, and what pH we're trying to keep that solution at is also going to be a factor. So first, the relative amounts of acid and base. In order for this to work, I said that we had to have about equal quantities of the acid and the conjugate base, or the base and the conjugate acid. And there's obviously a range in which that can work. We just did one where they weren't equal to each other. So what is that range? And it turns out that the most effective buffers, or for it to be a reasonably effective buffer, the relative concentrations of acid and base shouldn't be more than a factor of 10 apart. So if one is 0.1, the other one shouldn't be more than 1 or less than 0.01, for example. Okay. The absolute concentration of acid and conjugate base is also going to be important. So the more that you have in there, the more effective this buffer is going to be. And we don't have a specific number, but the more acid and conjugate base, or base and conjugate acid that you have present, the more it will be able to resist changes in pH. If you don't have very much of them present, then it's not going to take very much strong acid or strong base to significantly change the pH. All right, and then the final factor is the buffer range. So if you notice, all of the ones we did the calculations for, they were pretty close to the pKa value that we calculated. And so in order for a buffer to be effective, the pH that we're trying to achieve has to be within 1 pH unit on either side of the pKa. So if the pKa is 5, we could make a buffer with that acid and conjugate base that was between 4 and 6, but not any lower than that or any higher than that, because it wouldn't be effective. All right, so just to practice this skill, which acid would you choose to combine with its sodium salt to make a solution that's buffered at pH 4.25? And so for the best choice, you want to calculate the ratio of the conjugate base to the acid that's required to attain that desired pH. Okay, so we want a buffer that has a pKa, or an acid that has a pKa that's within 1 unit of 4.25. Okay, we have, we can easily eliminate chlorous acid because 1.95 is way below that, and hypochlorous acid has a pK of 7.5, so that's way above. All right, so that leaves us with formic acid, which is 3.74. That's about a half a pH unit off, and then we have nitrous acid, which is 3.34. And while that is within 1 unit, formic acid would be the better choice because it's closer. Okay, so in order to find out how much acid and base we would need, we want to use our Henderson Hasselbalch equation. So the pH is equal to the pKa minus the log of the concentration of base over the concentration of acid. Excuse me. So for this one, we're going to plug in 4.25 as the pH. And we want our pKa is going to be 3.74. All right, because we chose the formic acid, plus the log of the concentration of base over the concentration of acid. So we'll just solve for that ratio. So the log of the base over acid is equal to 0.51. So the ratio of base to acid should be 3.24. Okay, so that means we should have 3.24 times as much base as we have acid in our buffer solution. Okay, so the last thing is just a definition. So now that we know the factors that affect the buffer, let's talk about what buffer capacity is. So that's the amount of acid or base that you can add to a buffer without causing a large change in pH. Okay, and so the buffer capacity increases as we increase the concentrations of the buffer components, and it increases as the relative concentrations of the components is more similar to each other. Which is related to how close we are to the pKa for that particular acid. Okay, we're not going to calculate buffer capacity, but you should be able to think about this qualitatively in terms of which buffer is designed such that it will resist the change in pH more.